Hello and welcome to today's discussion on gravitational concept of electric current and its application of Gauss's law to understanding electric field near uniformly charged non-conducting sphere. First, let's explore the idea of electric field. Electric field is the strength of any charge that are positive or negative. These electric fields are responsible for exerting force on other charged object closer to it. In physics, we sketch lines vector coming out of or pointing towards the charge according to its type to visually study and understand the electric field. For positive, it points outward, and for negative, it points towards the charge. The area covered by the magnitude of these vector lines is called electric field, and the lines are the electric field lines. Electric flux. Electric flux is the measure of how much of electric field lines passes through the surface of any area that is closer to the charge or charge being enclosed inside it. Electric flux is calculated by taking dot product of electric field vector and the area vector. Area vector here is a normal line that is directed perpendicular to the surface and has same magnitude as area. Cos theta is the angle between electric field vector and area vector. As we can see here, both the vector are aligned with each other and make 0-degree angle. So the cos of 0-degree angle is 1. So the electric flux is maximum at 0-degree angle. And above this we'll have less and less flux, and finally when these two vectors make 90-degree angle there will be no flux. Gauss law. One of the foundational ideas of electromagnetic is Carl Friedrich Gauss' law. According to this law, when there is a charge enclosed inside a volume of the surface, electric flux will be equal to the total charge enclosed by the surface divided by permittivity of free space, which is denoted by E naught in the equation here. To pass this law, Gauss has defined three basic symmetrical surface, which is also called Gaussian surface. Those are spherical symmetry, cylinder symmetry, and planar symmetry. Today we are using spherical symmetry to our uniformly charged non-conducting sphere.
Let's use the Gauge's law to find the electric field outside of this sphere at point P. First, we need to draw an imaginary symmetric sphere from around the original sphere, so the charge of the sphere is enclosed and the law can be applied. Let's suppose there is a q amount of charge in the sphere. Total electrical flux is the integral of each field lines covering that tiny area, which can be written as the equation shown below. Here dA is the tiny little area that the electrical field lines occupy. We can take out the E of the integral as it is constant at any point as the sphere is uniformly charged, and we can remove cos theta as the angle between the electrical field vectors, and the area vector is 0 degrees, which equals to 1, as shown in the equation below. The integral of 1 dA is a, so our equation can be written as the equation below. Applying Gauss's law to find the electric field can be rewritten as E equals to Q enclosed over area times electric field strength. Field at point P outside the sphere will be as shown in the diagram below. Here, small r of the radius of the imaginary surface drawn over the sphere, so area will be 4 pi small r squared, and the total charge enclosed is Q, so electrical field. Therefore, in the equation below, E equals Q over 4 pi r squared times electrical field. To measure the electrical field inside the sphere, at point P, we draw an imaginary line out inside the sphere. This time the radius of the imaginary sphere is smaller than the original r.
To determine the electrical field inside the ununiform charged sphere, we draw an imaginary Gaussian surface in the form of a sphere with radius r less than the radius capital R of the actual sphere, which is illustrated in the image above on the top right hand side. The charge enclosed by the inner Gaussian surface depends on the volume charge density P, which is the total charge Q divided by the volume of a sphere, 4 pi r cubed divided by 3. Using the volume charge density, the enclosed charge is the density multiplied the volume of the inner Gaussian sphere, which is P times by 4 pi r cubed divided by 3. Performing the calculation gives us the enclosed charge as QR cubed divided by R cubed. We can plug this into the electric field equation derived from the Gaussian's law, which states the electric field multiplied the area by the Gaussian surface equals the enclosed charge over ellipse 0, which is E constant 0. Doing so gives us the electric field inside the sphere as E equals to QR over 4 pi r cubed, E constant. As expected, this shows that the electric field decreases linearly with increasing distance r from the center, since the enclosed charge is proportional to r cubed. In summary, applying Gaussian's law allowed us to derive an expression for the electric field at any point inside the ununiform charge insulating sphere. In summary, we have explored using Gaussian's law to determine the electrical field of an ununiform charged non-conducting sphere. By applying Gaussian's law, we derived an expression for the electric field outside the sphere. This showed that the field decays as expected for this spherical charge distribution. To find the electrical field inside the sphere, we use Gaussian surface of a radius r less than the sphere radius capital R. From the volume charge density, we calculated the enclosed charge and applied Gaussian's law to obtain the electrical field expression. This revealed a linear decrease in the field moving towards the center. The behavior of the electrical field lines and equations quantitatively demonstrates key properties of the electrical field near charged spheres. The direction and decay match expectations. In summary, electrical flux coupled with the Gaussian's law is a powerful tool for calculating the electrical field around the charged objects. When applied to the ununiform charged non-conducting spheres, it provides a straightforward way to find the electrical field at points outside the sphere. This principle is fundamentally in understanding and solving electrostatics problems in physics and engineering. In this slide, this is the reference, the key sources my team has referred in creating this presentation. Thank you for listening.